So today here we're proving things about quadrilaterals. Okay, I know that you believe me when I say that the quadrilateral with four right angles is a rectangle, but how can we prove that? Well, we do that by coordinates. Okay? So we're going to talk about how we show that the diagonals of a rectangle are congruent. Okay, that is one of the properties of a rectangle, is that their diagonals are equal. Okay, so what we want to do is we want to draw ourselves a rectangle on your grid here. Okay, so we always put a corner at the origin. That's a real easy coordinate, 0, 0. Right, that's probably the only number that we're ever going to use is 0, 0. Okay, so let's draw the horizontal side of your rectangle. And how far over to the right do you want to go? That's the question. Okay, and since this is general, you're not picking any numbers. Numbers are dumb. We don't have any numbers. Okay, because if you say 12, then you're only showing it for something that has a side length of 12. And that's one specific rectangle in the entire universe. Okay, we don't want to use one because that would be way too many things. Because then you have to prove it for 13, and then you'd have to show it for 14. And you have too many to do. So we're going to use letters to represent any number you ever want to think of in the world. Okay, so since we went along the x-axis, let's say that we went x units. Okay, you could use A, you could use W, you can use whatever your favorite letter is. So what are the coordinates of this point here that are x units away from the origin along the x-axis?
0,
X comma 0. Since we always go horizontally first in our coordinate system, you go x to the right and then 0 units up. Okay, so now let's draw the vertical side of our rectangle. Okay, so you know it has to have a 90-degree angle. So there we have it along your y-axis. So since we're going vertically, what letters should we use to represent this length?
Y.
Probably Y would be a good one, but once again, you can use whatever letter you want. So what are the coordinates of this point here? 0 in the x and some random length y. Okay? So then if we complete our rectangle, we have to draw this one parallel to the base and this one parallel to the left side. And then what are the coordinates of this point up here? X comma y. Okay, so whatever your favorite two numbers are, you can plug them in, and we'll show this numerically, but we're going to do this in general. So prove that the diagonals of a rectangle are congruent. So let's draw those in next. Your diagonal goes from corner to corner. Okay, so we're going to do this one first. We'll call this diagonal number 1. So we're going to use D as our variable and a subscript 1 to represent the first diagonal. Okay. So notice what kind of a triangle we form if we use the bottom and the right side. What kind of a triangle is this?
A right triangle.
This is a right triangle because in a rectangle all the angles are 90 degrees. And whose theorem applies in all the right triangles? Pythagoras'. So that's exactly what we're going to do. We're going to set up a Pythagorean relationship, okay, which says one of the legs, we'll call it x first, plus the other leg squared, which is y squared, equals the diagonal d sub 1 squared. Okay? And what we want to do is solve this equation for d sub 1. We want to isolate d sub 1. Okay? So notice d sub 1 is being raised to the second power. How do we eliminate something that's being squared? We square root it. Squaring and square rooting are opposite operations. So whenever something's squared and you want to unsquare it, you take the square root. Okay, and that's really all that we have to do. So the diagonal is found by taking the square root of whatever your x coordinate is squared plus whatever your y coordinate is squared. Okay, that is the length of d sub 1. Okay, I know it's not very satisfying. Right? You can't go to the store and buy something with that amount of money. It's an equation, but it is in fact correct. Okay, so now the second thing we want to do is try for the other diagonal. So here is your other diagonal. And we're going to call this one D sub 2, right? This is the second diagonal of our rectangle. So it's D sub 2. And once again, we have another right triangle. So whose theorem are we going to use to find the length of this hypotenuse? Once again, Pythagoras'. So let's see what we have. Let's use the base length is x, so we square that length, plus your other length is y squared, and that equals d sub 2 to the second power. And once again, how do we solve a square? We square root it. Okay? So that means that d sub 2, the second diagonal, is found by taking the square root of whatever your x value is squared plus whatever your y value is squared. So now we're going to take a look-see at what we have just done. Do these equations look exactly the same? Yes. So no matter which x and y coordinates you pick, no matter what lengths of your rectangle you pick, if you find the diagonals, they are going to come out to be the exact same. Okay? If your equations are equal, that means your lengths are equal for whatever numbers you pick. Okay? No, it's not very satisfying, but this is a coordinate proof. We have just shown using an algebraic equation that the lengths of your diagonals come out to be the same. No matter which two letters you pick for x and y, whatever two numbers you have, you're going to do the same operation to both of them. Okay? That's all. That's all you got to do. I know. What? That's all? Of course. That's a lot, right? It's a lot of stuff. Number 2 then. Prove that the diagonals of a parallelogram bisect each other. Okay? So let's draw in our parallelogram. One corner goes here at 0, 0, at the origin. Okay? Now, here we're moving in both the right and the left direction. So if we go up here to whatever coordinate this is, we have to make a choice, right? How high have we gone in the y value, and how far to the right have we gone in the x direction? Okay? So you can use whatever letters you want to, but let's start at the beginning of the alphabet. Let's call this length A, and let's call this height B. Okay? Once again, you can pick whatever letters you want. So what are the coordinates of this corner right there? A, comma, B. We've gone A units to the right and B units up. Okay? So now we have to decide how far to the right do I want to go. Okay, to get to the bottom side of my parallelogram. So this much is A. How much more do you want to go? You want to go C units? That sounds like an excellent way to go. So this is going to be C units. C units represents the end of A to the coordinate point right there. Okay, remember, it's another length, so it's another letter. So what are the coordinates of this point here?
A plus C.
A plus C. We add those two lengths together, and how high have we gone in the y? 0. Okay, so we have gone A plus C. Right, so this length here is we're calling C. And if you start at the origin and go all the way to the right, we have to add these two segments together. A plus C. Okay, now we have one other point to decide, and that point has to be out here in order to have a parallelogram. Okay, and what we know about parallelograms, the top length has to be the same as the bottom length. Okay, so what is the length of the bottom?
A plus C.
A plus C. So we have to go another A plus C up here. Okay, we have to go another A plus C up there. So let's draw that in here. A was this much about, right? This is A units from here to here. And then this one was B units, or C rather, from here to here. So then what are the coordinates of this point right there?
A plus C, comma B.
Hang on. Don't forget about where we've already gone. So we've already gone this much, right? How much is that we are already away from our y-axis? That is also a units. Okay? So then from the beginning, from the y-axis, right, from 0 in the y, or the x, how far have we gone to get to the final thing over here?
2A plus C.
2a plus c. We have gone 2a lengths, and we have gone 1 c length. And how high have we gone in the y direction? B. We've gone b units up. Okay, so when we come back here, right, we can kind of draw, so we can look at this as a triangle, right? So we have a right triangle that we kind of get to there. And then we have like another, right, we have another right triangle on this end. Okay, where if you want them to be parallel, they have to match. Okay, now if you didn't care about parallelness or lengths or anything, they would be any letters you want. Okay, but we want them to be the same because it is a parallelogram, and part of the properties of parallelograms are your slopes are equal. Okay, so we have to make sure the slopes are equal. These are easy, they're zeros. Okay? Okay, so now that we've done the hard part, this is the hard part. This is not easy way of thinking. You don't often think like this. And why would you, by the way? Right? You have no reason in your life to think. This doesn't help you clean your room. It doesn't help you drive a car. All right? It doesn't help you earn money, usually. It doesn't help you mow the lawn or do your laundry. But, right, this is the way it works. So what are we asked to do? We are asked to show that the diagonals bisect each other. Okay, so let's draw in our diagonals. There's a diagonal 1, right? There's our pink diagonal. And let's draw our other diagonal and make it purple. Okay, so basically we're trying to show that that point is a midpoint. Okay, if we can show that these two lengths are equal, then it's in the middle. And if we can show that these two are equal, then that means it's in the middle. Right? To bisect means to cut in the middle. And if it's in the middle, that means the lengths are the same. So the length from the origin to the middle is the same as the length from the middle to the end. And we're going to do this with formulas or equations. Okay? I know, kind of hard to imagine that this is actually going to happen. So let's use the midpoint formula. Okay? If you want to show that it's a midpoint formula. So we do that by adding our two x values together and dividing by 2, and then adding your two y values together and dividing by 2. Right? That's how we find a midpoint. Okay? So if I can show that the coordinate of the midpoint of the purple line is the same as the coordinate of the midpoint of the pink line, that means those would be the midpoints of each other. Right? If the midpoints of two lines are the same coordinate, then they're midpoints of each other. So that's what we're going to try and do here. I know, it sounds like a big ask, but let's do it. Okay, so let's do the pink one first. So we have x1 minus x2. So here's one x coordinate, and this is the other x coordinate. Okay, so we have 2a plus c plus 0 divided by 2. Okay, and then the same thing for the y coordinate. We have b plus 0 divided by 2. So we can simplify that a little bit by getting rid of the zeros. Okay, those are kind of just sticking out there. So 2a plus c over 2 and b over 2. Okay, so that's the coordinate of the midpoint of my pink line. So we're going to do this similar type of a thing for the purple line. Okay, we're going to add our x's together and divide by 2. We're going to add your y's together and divide by 2. So let's see. This x is a, and this x is a plus c. So we have a plus c divided by 2. And then our y-coordinate was b plus, what's the y-coordinate of the second purple line? Right here? 0 divided by 2. Okay, so let's do some simplifying. A plus a is 2a plus c divided by 2. And then, of course, b plus 0 is just b. And look at what you see. Those are the exact same formulas for both midpoints. So that means they both have to be the same thing. Okay? It's kind of an aha moment, right? This works out just fine when we put in the correct coordinates. So picking your coordinates is the hard part, because you have to make sure that your things are even or your things are equal. Okay? You can't just go any random length and have it be a parallelogram. You have to do it specifically with specific lengths. Okay, in this case, specific letters. So we're going to do the same one with our last thing, prove that the diagonals of an isosceles trapezoid are congruent. Okay, so isosceles trapezoid has one set of parallel bases and two congruent legs. Right? And it's the fact that they're congruent is what makes this a true principle or property. So once again, let's put one coordinate at 0, 0. Okay, one of them always goes on the vertex. Okay, and then we go to our next point. So once again, how far in the x direction do you want to go, and how high in the y direction do you want to go? Okay, so you pick whatever two letters you want. Let's pick W and V. V and W, Volkswagen. So what are the coordinates here? My first point of your isosceles trapezoid. W, comma, V. All right, so this is the first leg here. And then how far to the right do you want to go? Right, pick another letter. You want it to be U. Well, I hope your U's and your V's are definitely different. So let's go. That's fine. We can go U right there. So then what is this coordinate here in the top right?
X.
W plus U, comma, V. Right, W plus U. So that's how far we've gone on the X. We've gone W, and then we've got another U units. So if I want my figure to be an isosceles trapezoid, how much more do I have to go in order to get to the end? Right here, how much more is this length? That has to be another W, because I need these things to be equal, right? These have to have the same triangles in order for their lengths to be the same. So I've gone W and then U and then W. So what are my coordinates? 2W plus U, comma, 0. Right? So the first part is putting them together with some coordinates. This is not an easy thing to do. Right? Nobody's ever asked you to do this, to my knowledge. To your knowledge? Has anybody asked you to do this? No? Your dentist didn't ask you? No? Your pediatrician? Was it like, hey, let's prove that? No. Nobody would do that. Right? Only me, the mean person, the math teacher. So we want to show that the diagonals are congruent. So here, let's draw in a diagonal. Here is one diagonal. Okay, and what's the easiest way to find a length? Pythagoras. Okay, so we're going to drop a vertical line directly down from that W plus U to make a right triangle. Okay, so we're going to figure out what this length is using the Pythagorean theorem. Okay, so let's look at Pythagoras. D sub 1 squared equals. What is the bottom length of my right triangle?
U.
W plus U squared, right? The whole entire length I have to square. So W plus U squared plus what is my height?
V.
V is the height, V squared. So that's the length of the first diagonal. We saw by taking the square roots. So D1 is the square root of W plus U squared plus V squared. Now, if you really want to be algebraic, you can multiply that out, but that's just a little ridiculous. We don't have to do that for our purposes. That's our equation for the length of the first diagonal. So now let's come in here and find the length of the second diagonal. So once again, we're going to drop a vertical line and create a right triangle. Okay, right triangles are very handy things, which is why we spend so much time studying them, because they can help us do lots of other things, mathematically speaking. I mean, they won't help you get a girlfriend. Maybe they will. Those tutor buddy that you fall in love with, and she falls in love with you magically. So the second diagonal squared equals, what is the length of the bottom of my right triangle? U plus W squared plus, what is the height of my right triangle? V squared. So now we're going to take the square root of both things and get the square root of U plus W, which is the same as W plus U, right? Those are equal because addition is commutative. So W plus U and U plus W, those are the same. And plus V squared, that's the same. So what have we shown?
They are the same.
That the equations for the diagonals are the same, which means that they must be equal to. So no matter what letters, your numbers you pick for V and W and U, you're always going to come up with the same length for your diagonals because the equations are the same. There's no way that they can be anything else. Okay? So this is how we prove things in geometry in general, with letters and equations that we want to make sure that they match up and are equal to each other. Okay? Wonderful job.